Dear audience, thanks for coming to our tutorial on image retrieval in the wild. Next, I would like to share a specific image retrieval task. In this task, we set certain persons as the retrieval targets. My name is Zhen Wang, a JSPS fellowship researcher working at National Institute of Informatics, Japan. It's my pleasure to share this tutorial with you. My presentation topic is Beyond Intra-modality Discrepancy, a survey of heterogeneous person re-identification. My presentation includes three parts. The first part is about general person re-identification. I will introduce what is person re-identification and its applications. We can also name this task as homogeneous person re-identification. The second part is heterogeneous person re-identification. It is the main part of my presentation. I will introduce four kinds of applications and their representative methods. In the third part, I will conclude by a discussion of existing works and some future research directions. Nowadays, millions of surveillance cameras are installed in the city, and they produce a large number of videos every day. It is of great difficulties for investigators to search for a criminal suspect when a criminal case happens. Here is an example. In a case in Nanjing, China, 1,500 police were asked to watch videos and find clues. They cost 1 month's time and finally find 329 shots related to the suspect. It is very time consuming. Person re-identification is a kind of civil technology to handle this problem of person image retrieval and to enhance the retrieval efficiency. It uses the person's appearance to match individuals across a group name of non-overlapping cameras or videos. Person re-identification can be also considered as a specific image retrieval or instance search task, and it is a variable topic that can be used in other real applications. For example, if we can find the same person in the surveillance camera network, we are able to track a person or record the location of a COVID-19 infected person. We can also find the person of interest from a large number of TV series so that we can quickly watch the video we like. In a shopping mall, different persons wear Google Glasses are able to cooperate with each other to find some persons of great interest. When a robot guides the road for us, the robot can focus us again even though we move to the other places for a while. General person re-identification just counts the challenge of intra-modality discrepancies or appearance changes in RGB images. Here I show some examples. The person's appearance may change because of the occlusion, the illumination change, and the viewpoint or pose change. To address the problem, existing methods use this diagram of person re-ID. For the probe image and gallery images, we extract the features by person representation mode. Then the features are compared by similarity or distance measure mode. After we obtain the ranking result, we can use the re-ranking method to optimize the list. In recent years, we have made significant advances in general re-ID. The performance is very high on some public datasets. For example, we can obtain 96.1% rank 1 accuracy on market 1501 dataset. It even outperforms the human ability on finding the target image in the image dataset. It means that the intramodality discrepancy has been well addressed. However, the general re-ID assumed an ideal scenario for privacy. Well, all person images are captured in the daytime with visible spectrum and have sufficient details to represent a person. In real-world applications, however, it is impractical to assume the data source is always in such a desired modality. Let's focus on a more practical person retrieval, heterogeneous person re-ID. In this presentation, we mainly focus on four categories: low resolution and high resolution matching, infrared and RGB image matching, sketch and photo matching, text and image matching. For instance, in order to find a suspect, the system may have to check person images in low resolution that are generated by older devices or captured by infrared cameras when the illumination condition is not so sufficient. Moreover, witness descriptions in terms of text and sketches drawn by artists should also be used as the clues. These scenarios face challenges beyond the intra-modality discrepancy. To improve the practical ability of ReID system, we should make more efforts to bridge the gap between different camera settings, between different sense devices, and between reproduction of human memory and direct recording by a camera. Note that we don't refer to RGB depth-based ReID, since in real applications, the depth channel works as the complement for the RGB channel, and a depth image of a person will not be used to retrieval in an RGB image gallery. As we know, ReID attracts much attention in the research community. To our knowledge, there are few viewers in this field. The paper 10 explored the ReID applications built on gate sequence. It is a special and different focus. Paper 11 focused on general ReID and made a multi-dimensional overview. Paper 12 provided a systematic evaluation with different features and metrics. Paper 13 started to look into some intermodality challenges, but provided a limited summary of some efforts and problems. Here, we would like to provide a summary of current heterogeneous ReID research from different views. We make a comparison between Homo ReID and Hetero ReID. For the media type, Homo ReID only explores desired RGB images, while Hetero ReID takes additional low-resolution infrared sketch images or text descriptions into account. For the participant, Homo ReID only explores the resources from machine intelligence, while Hetero ReID also brings in the input from human intelligence, such as sketch images drawn by painters or text descriptions by the witness. For the main challenger, Homo ReID only needs to deal with the intramodality discrepancy, while Heterogeneous should bridge the gaps from both intra and intermodality discrepancies. There is also a big performance gap between Homo ReID and Hetero ReID. We feel that it is the right time to call for more attention and research effort to this important and still large uninvestigated area. ReID system always consists of a feature extraction part and the descriptor matching part. For Homo ReID, both probe samples and gallery samples are from desired modality that are daytime visible spectrum and high resolution images. While for the Hetero ReID, the probe samples and gallery samples or gallery samples are from another modality, since additional intermodality discrepancies are larger than intramodality discrepancies. Hetero ReID is more challenging, as inter and intramodality discrepancies are essentially different. The method designed for Homo ReID cannot be directly used in Hetero ReID. We summarize available datasets for heterogeneity in the table, including the application scenario, the total number of cameras, identities, and samples. To make a comparison, we also list the two typical homogeneity datasets. The heterogeneity datasets are categorized into four types. We have the following summaries. Although many low-resolution datasets were constructed, most of them are simulated. Only two infrared datasets were constructed. SYSU-MM01 is an active infrared dataset, while RegDB is a passive one. Only one sketch photo dataset and one text image dataset were constructed. Compared with homogeneity, there is still a lot of room to construct more available datasets. For low resolution, it requires to construct practical datasets instead of the simulated ones. For the other three kinds of application scenarios, datasets under different conditions, scales, or with large scales should be constructed. So let's see how we address the new intermodality discrepancies under existing public datasets. At first, we focused on the low resolution LR to high resolution HR discrepancy. The LR image has limited information to represent a person. The person's appearance degrades in a less detailed modality. The first work I want to introduce is multi-scale learning for low-resolution person reality in ICCV 2015. This is the first work focusing on the low-resolution to high-resolution reality. The method focuses on match learning to match images with different resolutions. For each image, the method first obtains two images. One is HR and the other is LR. Then the method proposes two projections, one for HR and the other for LR. It assumes that the structure of data distribution of a person's appearance across high resolution and low resolution are similar in the feature space. So after projecting the image features of different scales into a common space, the method satisfies this cross-scale alignment. Here, they propose a heterogeneous class mean discrepancy as the objective. WH and WS are the two projections. The experiments show that existing machine learning modes have a clear performance drop, but the proposed multi-scale metric works. The second work I want to introduce is super-resolution person re-identification with semi-coupled low-rank discriminate dictionary learning in CVPR 2015. The method learns a pair of low-resolution and high-resolution dictionary and a mapping function from features of the training sample. With the learned dictionary pair and the mapping function, the features of low resolution can be transferred to high-resolution features. The assumption is that there exists a dictionary pair over which the representation of two modalities have the stable mapping. Here, a discriminant term is designed like triplet to make the transferred HR features of low-resolution images be close to the features of the HR images from the same person, but far away from the features of HR images from different persons. And also, a low-rank regularization is introduced to ensure that the learned dictionary pair can well feature the space. Experiments show that these two terms are very useful for the feature transfer. The third work I want to introduce is our work on EJCal 2016. We propose a new representation between different resolutions. We investigated the distance variation behavior by changing the image resolutions or scales. We observed that the scale distance functions generated by image pairs from from different persons or same persons can be separated or classified, as the red and the blue regions indicate. The scale distance functions are further represented by parameter vectors in the scale distance function space. We map a function onto the function space and classify it as either feasible or infeasible by random forest. Experiments show that we can use this kind of scale distance function to represent an image pair. The first work I want to introduce is deep low-resolution person re-identification. The method is very straightforward. It consists of a super-resolution network and a re-ID network. The low-resolution images, the downsampled low-resolution images, are enlarged by super-resolution network. Then two kinds of output super-resolution images and the original high-resolution images are input into the re-ID network. The network is in an end-to-end way, and the joint loss function is used to optimize the CNN architecture. The key strategy of this method is unifying the modality to high resolution and the match images in high resolution modality. The fifth work I want to introduce is our work on EJCAD 2018. This work also explores a modality unification strategy. We cascaded multiple SR GAN in series so that the network is capable of enlarged LR images with different scales. To supplement the ability of image feature representation, we plug in a re-identification network. An end-to-end framework improves the integration between scale-adaptive super-resolution and the re-identification, and consequently enhance the similarity of LR-HR pairs during the super-resolution process. In addition, a common human loss is designed to make the SR image look more like a human. Here, we show some generated images. The sixth work I want to introduce is resolution invariant person re-identification in EJCAD 2019. To enhance the super resolution, the method proposes a foreground focused super resolution module. Here, in the formulation, M is the mask of the foreground. The resolution invariant feature extractor is used. It consists of several dual stream blocks. Each learns resolution invariant features through two CNN streams. Features from two streams are fused with weight learned by the resolution weighting loss LR. The module finally outputs the features, which are used to compute the cross-entropy loss LX. And the experiment shows that the foreground focus and the dual stream blocks are useful for different resolution image matching. The seventh work I want to introduce is recovery and identify, a generative dual model for cross-resolution person re-identification in ICCV 2019. The method introduced an adversarial way to enhance the generation. Overall, the network consists of a cross-resolution GAN and a cross-modal re-ID network. Cross-resolution GAN learns the resolution invariant features and recovers the missing details in the LR input images. Cross-modal re-ID network considers both feature modalities for cross-resolution person re-identification. Note that the network includes two discriminators. The feature discriminator DF takes the feature FH and FL as the input to determine whether they are from feature XH or XL. The image discriminator DI takes the recovered HR images and the original HR ground truth images as input to distinguish whether the input images are real or fake. Experiments shows that the two discriminators for feature and images are very useful. The eighth work I want to introduce is Inter-task Association for Cross-Resolution Person Re-identification in CVPR 2020. The method above combines super-resolution module and the ReID module together, but in this paper, the authors consider that super-resolution module and the ReID module in a cascaded manner is unsatisfactory. Suppose the main task is ReID for high-resolution image and generated super-resolution images. The auxiliary task is super-resolution. The method proposes a inter-task association module between the identity representation Fc and the discriminator representation Fd. In this way, the method recovers the resolution of LR quell images in such a way that super-resoluted image can well match high-resolution gallery images for person re-identification. We will compile this uh, LR-based method later in the discussion part. Next, let's focus on the infrared IR to RGB discrepancy. The modality gap is more challenging since the discrepancy between low resolution and high resolution is only on RGB channels, while the discrepancy between IR and RGB are in different channels. The first work I want to introduce is RGB infrared cross-modality person re-identification in ICCV 2017. This is the first work focusing on the IR to RGB re-ID. The authors analyzed three different network structures. They are respectively one-stream, two-stream, and asymmetric FC layer. And it is found that one-stream network can learn and involve domain-specific structure if there exist domain-specific and shared nodes. Based on one-stream network, the authors also propose a deep zero padding to help one-stream network more likely involve domain-specific nodes automatically, so as to make the network structure more suitable for the task. The second work I want to introduce is hierarchical discriminative learning for visible thermal person re-identification in AAAI 2018. The proposed network contains two stages, feature learning and metric learning. The feature learning aims to learn multimodality shareable feature by a two-stream serial network containing with identity loss and constructive loss. The metric learning focuses on discriminative metric model, learning with modality-specific and modality-shared metrics. Experiments shows that both feature learning and metric learning work. The third work I want to introduce is our work in EJCAL 2018. We present an end-to-end dual-path learning framework and a novel bidirectional dual-constraint top-ranking loss to simultaneously consider the cross-modality and intra-modality variation. Note that the weights of embedding FC layer are shared with each other for multimodality shareable feature learning. The ranking loss consists of two parts. They are cross-modality constraint top ranking loss and intra-modality constraint loss. Experiments shows that the end-to-end framework works better than two-state framework. The first work I want to introduce is cross-modality person re-identification with generative adversarial training in EJCAL 2018. The proposed network consists of two components. The first component is a deep serial network as a generator with identity loss and cross-modality triplet loss to generate modality invariant features for RGB and IR images in common subspace. The second component is a modality classifier as, as discriminator that discriminates between different modalities. The discriminator and the generator beat each other to learn discriminative common representation for person re-identification. The fifth work I want to introduce is our work in CVPR 2019. We try to unify the modality. The framework consists of two parts. The image level discrepancy reduction subnetwork TI first projects inputs from the image space to the unified space. Well, the modality discrepancy is reduced. After translation, we can obtain four-channel images. Then, the feature level discrepancy reduction subnetwork TF is utilized to eliminate the remaining appearance discrepancy. The two subnetworks are cascaded and jointly optimized in an end-to-end manner. The sixth work I want to introduce is infrared visible cross-modal person re-identification with the X modality in Triple AI 2020. The method proposes an auxiliary X modality. A lightweight generator outputs the X modality images. Then, three modalities are fed into the weight-sharing cross-modal feature learner. Two constraints are designed to constrain feature representation and classification outputs, and to learn cross-modality information of three modalities in a common feature space. They are the cross-modality gap, CMG, and the modality respective gap, MRG. Note that the modality respective gap, MRG, is indeed the intra-modality discrepancy. The seventh work I want to introduce is high CMD, hierarchical cross-modality disentanglement for visible infrared person re-identification in CVPR 2020. The entire framework includes two important components. The hierarchical feature learning module extracts identity and attributes features. The ID-preserving person image generation network is to disentangle ID discriminative factors and ID excluded factors from cross-modality images. The ID discriminated factors include body shape and clothes patterns, and ID excluded factors include pose, emulations from RGB and IR images. The network is in the attribute exchanging strategy so that the ID excluded factors are disentangled. The eighth work I want to introduce is cross-modality person re-identification with shared specific feature transfer in CVPR 2020. The method extracts two streams features. Then the authors propose a feature transfer method by modeling the intramodality and intermodality affinity to propagate information among and across modalities according to their neighborhoods. This can effectively utilize the shared and specific information of each sample. In the picture, the green, yellow, and blue features stands for the RGB, IR, and shared features. Z stands for the propagate features. Meanwhile, a complementary learning method is used to extract discriminative, shared, and specific features. Then let's focus on the text-to-image discrepancy. In this task, we use text or neutral language to find some certain person. Actually, some works investigated to use attributes or some separate words to find certain person, as adversarial attributes image person re-identification in EJCAL 2018 does. The method learns a joint space and it used in the utilized adversarial mode to generate image concepts. Person search with natural language description in CVPR 2017. is the first work to study the problem of searching person with natural language. To address the problem, the method consists of a visual subnetwork, as the right blue branch indicates, and the language subnetwork, as the left branch indicates. The visual subnetwork generates a series of visual units. Each unit encodes if the certain appearance pattern exists in the person image. Given each input word, the language subnetwork outputs word-level gates and unit-level attentions for weighting visual units. Then the visual units and words are matched with weights. What I want to introduce is identity-aware textual visual matching with latent core attention ICCV 2017. It is a two-stage deep learning framework. The stage 1 network can effectively screen easy incorrect matching and also act as the initial point for the training stage 2 network. The stage 2 network refines the matching results with binary classification. The third work I want to introduce is deep cross-modal projection learning for image-text matching in ECCV 2018. The method proposed two losses to learn a joint feature embedding. The first loss is cross-modal projection matching loss. It attempts to minimize the KL divergence between projection competitive distribution and the normalized matching distribution. The second loss is a cross-modal projection classification loss. It attempts to classify the vectored projection of the features from one modality onto the matched features from the other modality. The fourth work I want to introduce is improving deep visual representation for person re-identification by global and local image language association in ECCV 2018. The authors propose to use language descriptions as training supervisions for learning more discriminative visual presentation for person re-identification. They provide two effective and complementary image language association schemes. They utilize semantic and linguistic information to guide the learning of visual features. The overall framework employs the ResNet 15 as the backbone architecture. The produced intermediate features is associated to the description T by the global discriminative association part, and, and it is also associated to the phrase feature P by the local reconstructive association part. Finally, let's focus on the sketch to photo discrepancy. This is the only one representative work in these directions, cross-domain adversarial feature learning for sketch re-ID in ACM Multimedia 2018. The network has two feature generators for sketches and photos, respectively. Then two features are fed into a domain discriminator. The losses output the domain discriminator are two opposite objectives. Meanwhile, two intra-modality classifiers are trained for the person-level classification, and the pairwise verification network is introduced to judge whether they are from the same person or not. Finally, let's go to the discussion. We can find that most of the methods selected a deep learning framework. It is probably because all the heterogeneous application scenarios are raised in recent years, and deep learning methods are in their high-speed developing period. In general, when a significant amount of training samples are available, deep learning methods are good at learning shared feature and classification. We can also find that different methods have different focuses. To fill gaps between the desired modality and other heterogeneous modalities, some methods try to learn a metric, Others attempt to learn the shared features. And there are also methods unifying the modality on the data level. In the slides above, I have made a mark to indicate their focuses. However, the existing researches in each application scenario still have limitations. For the low-resolution application scenario, recent works are mainly evaluated on the simulated datasets. For the sketch application scenario, only one method touched this direction due to the hardness of building a benchmark. So we still have a long way to go. As described above, in our opinion, representative methods can be categorized into three kinds of learning pipelines. The picture shows the diagram of each pipeline. Pipeline A employs the metric learning method to learn how to match features from separate representation learning modes, and the representation learning modes are trained separately with single modality samples. Pipeline B focuses on learning shared feature modes of different modalities, and training data come from both modalities. Pipeline C pays attention to generating the unified modality samples. For example, using a super resolution method to generate high resolution images from low resolution images, or using some image generation method to generate infrared images from RGB images, and also generate RGB images from infrared images. This table compares representative methods we introduced above. We use this table to make some useful tips. We can see that for each kind of application scenario, from top to bottom, the method becomes more effective. Generally, pipeline modality unification performs better than pipeline representation learning and better than pipeline metric learning. Hence, unifying the modality of samples is an effective way to fill the gap. Since we have two modalities, the adversarial learning is also an effective way to make the network adapt to different modalities. In addition, personal re-identification is a kind of fine-grained retrieval task, so it is suggested that we should pay attention to the details of the person. And the intermodality gap and the intramodality gap are usually reduced by two different networks as two different tasks. It is better to make a connection to let them benefit each other. Finally, let's make a discussion of future directions. The first one is data construction. For the low-resolution application scenario, the researchers can only get simulated datasets. For the other types of application, although the researchers can achieve practical datasets, the choice is limited. In addition, large-scale datasets are also required. It is somehow urgent for us to build new datasets and push forward this research area. On the other hand, generating more realistic datasets like Paper 5 is also a good way to make one step forward. The second one is taking advantages of homoready datasets and methods. There are sufficient datasets and methods in homoready. It is easy to address the intramodality discrepancy in the desired modality. Obviously, the feature space of the desired modality can be well constructed. Since the heterogeneous modality samples are not enough, it is hard to build a perfect heterogeneous feature space. However, it is reasonable to project these samples to the desired modality space, as paper 36 does. The third one is human interaction and crowdsourcing. For sketch and text application scenario, human intelligence join into the process of re-ID. Human intelligence is sometimes subjective and incomplete, so we should consider how to mine and investigate useful information to help search the target in the surveillance system. On the other hand, a lot of witnesses will provide their clues. Each person may have a different view, so that a crowdsourcing Crews may be diverse with each other. We should design a strategy to remove conflict and filter valuable information. Fourth one is investigation on the modality unification. For low-resolution application scenario, some methods attempt to use super-resolution technology to unify the modality. For IR application scenario, with the help of cycle gain, one work not only transfer the image from IR to RGB, but also from RGB to IR. However, for the text and sketch application scenario, no work has investigated to unify the data modality. And on the other hand, we can also investigate to unify the modality to a latent modality. For example, a middle level resolution for low resolution application scenario. The fifth one is integrating multiple heterogeneous application scenario. For a practical system, it may require different kinds of input to search out the target. The heterogeneous application scenario can be equipped in different stages. If we can integrate different kinds of input, more valuable information could be used for the retrieval, since different inputs may have different attentions and views for the target. It also will raise a novel multiple cross-modality retrieval research task. The sixth one is considering the privacy issue. It is fine to conduct academic research on public datasets, but with the leak of personal image data, privacy concerns are raising nowadays when algorithms need to be applied to practical applications. Recently, some works have exploited to hide some privacy information in the image. For heterogeneous reality, since it contains multimodality data, personal templates of different modality or latent modality should be investigated to protect. At last, I would like to thank all the cooperators for this survey. Thanks very much for your patience.